Here's some more folks. Hello, friends. Welcome back on this rainy day. But hey, we don't shovel rain, do we? Yeah. I can see my driveway again for the first time since December. It's excellent.
Happy Pi Day also.
Happy what?
Pi Day.
Happy
Pi.
Oh. Yep. Happy Pi Day. Yes, thank you. 3.14. Yes, it took me a minute too. It's like, what day is it? It's my Aunt Marcia's birthday too, so happy birthday, Aunt Marcia. Not that she's going to be watching this, but just, putting that out there. So yes, we were talking about modeling bendy patterns of change, right? Heading past just the idea of linear. So time in particular, if you have more than 3 or 4 occasions, odds are good you have some kind of nonlinear trend that you may need to consider. So these are various options for doing so that we're talking about. So let me do some reviewing, get us back in the mood here. So 2 baseline models that are important in thinking about the alternatives to compare this to. Is the lighting in here different than usual? Do I need to turn this down? It feels like it's really bright up here. Let me see that one. There, is that better? Or is that too dark?
More romantic.
More romantic. Said no one ever about my class. Well, I tell you what, I'll make you a deal. We'll keep it low so that there's no eye strain. But if any of you falls asleep, I reserve the right to come over and poke you with this. I started carrying one of these ever since I was a postdoc and I wanted to feel professorial. Having a pointing stick really helps. You can also jab somebody if they're not listening. So deal? Deal. Okay, yeah. Especially when you're a young professor who's more likely to be mistaken for a student. You need everything you can get to look more professorial with the big sticks. So I highly recommend one of these babies. But anyway, yeah, I'm going to use it today. Why not? Let's do it. So these are our 2 baseline models. The problem is that the folks at home can't see my stick. See, I speak softly and carry a big stick. That's the saying. But that's why we'll get the mouse on here for their benefit. So the red line. That's the prediction from an empty means model that has only a fixed intercept. No matter what kind of data you have, you can always start with that. That's the simplest possible model you could have with respect to time. It says there is no trend over time. That's probably a reasonable thing if you're dealing with fluctuation types of data, where the goal is not to measure change. The goal is just to see how people vary within themselves over time. The black line is the prediction from the saturated means or the ANOVA model, in which time is treated as a categorical discrete predictor. So this is the answer key. This is as good a fit as it gets. It's a descriptive model in that you have 6 parameters to perfectly fit the 6 means. So you could just stick with that. And in certain situations, that's the most reasonable thing to do. We'll talk about a few examples of those in the next section on piecewise models. But this is only possible to fit as the answer key, the saturated means, if you have balanced data. Otherwise, if you try to fit this, it's going to try and estimate a separate mean for every unique value of time that's in your data set, and the model can actually blow up if you have too many. So in practice, if you're dealing with unbalanced time, if you're dealing with a data set in which people are not measured at exactly the same times, for descriptive purposes, just so that you can get a sense of what the shape of the trajectory is you're trying to fit, you can round time into convenient intervals, nearest day, nearest week, nearest month, whatever makes sense, just to make a picture. But you would not do anything with that model otherwise to compare it, because rounded time is introducing measurement error. It's not a good idea. It's just for descriptive purposes, because having a picture lets you know where you're headed. So then our goal is to find some kind of fixed effect of time, some kind of trajectory that approximates this pattern through the means, hopefully spending fewer than 6 parameters to do so. Now, why would we want to do that? What's wrong with just having 6 means? I've gotten that question before, and it's a reasonable one. Nothing. There's nothing wrong with the saturated means model. I got 6 means. The problem comes in trying to describe change over time and trying to predict change over time. Because when people phrase research questions in longitudinal studies, it's usually, I want to see if blah, blah, blah predicts change over time. They're not interested in the change from 1 to 2, and 2 to 3, and 3 to 4, and 4 to 5, and 5 to 6. They're interested in change, which implies some sort of function that is allowed to differ between people. So it can be more theoretically informative and more parsimonious to try and find a function that fits the means as best you can, and then we can look at individual differences in the function as random effects and predictors thereof. On the variance side, we're doing the same kind of thing. So the y-axis of this picture is variance instead of mean RT across time. The simplest possible model for the variance that we would entertain for longitudinal data has an E residual, because we've always got that, plus a random intercept. That says, that's the blue line here, that the total variance is predicted to be the same across time. The only way that can happen is if everybody changes the same, if growth curves are parallel. Otherwise, variance has to change over time, and what's not shown here, but goes along with it, is that covariance changes as a function of time too. So the black line is, again, the answer key. It's from the unstructured model for the variance, in which we estimate a separate variance and covariance for every possible data point in that matrix. So this is the pattern that our random effects of time are trying to mimic. If you have a random linear model, that implies that variance changes quadratically over time, parabolically. If you have a random quadratic time model, that implies that variance changes as a function of time to the fourth, or quartically. And so each of these additions of random time slopes of some kind, whether it's linear, quadratic, or otherwise, implies some kind of change over time to the variance and covariance. So this is the answer key. This is what we're trying to get to. This is only possible when you have balanced data. Otherwise, you don't know where you're headed, and you just kind of have to do the best you can. So if, let's say, you are reporting the results of a growth model, you're doing this kind of thing, and you have unbalanced data. So whether you run your growth model in mixed, as we're doing in class, or whether you use M+ or some other kind of SEM software, you set it up as latent variables instead, you're not going to get absolute fit statistics. It's not going to be provided for you in SEM once you tell it that people have their own time metrics. And if reviewer 3 goes back and asks you, why didn't you report fit? You're going to have to explain to them, I can't. In instances in which your total data can't be summarized by a single matrix, there is no way to judge absolute fit, because it's a moving target as to what the right answer is. Each person would need their own correct V matrix that's based on their own set of individual time values. So the moment that we move away from a common time schedule, a common set of DVs, we move away from the potential to fit the answer key and to test absolute fit. But we can always do relative fit. We can always say this model fits better than an alternative. We just don't necessarily know if we're all the way there yet. So, with me? Okay, so that's what we're doing. We talked about quadratic models, and here's a picture that is useful. A quadratic time slope takes the linear time slope and it does one of 4 things to it. What are they? We'll go around the room. Give me one of them. A quadratic time slope takes the linear time slope and does what to it? Multiplies it by, twice the quadratic is how the linear changes. But what are the 4 kinds of patterns of change that are depicted on here?
Possible slope and possible linear slope, possible quadratic slope.
Right, so what if you have positive, positive?
So there.
Yeah, that one, right? The quadratic slope takes a positive linear slope and makes it more positive as time goes on. That's one option. Or the quadratic can take a positive slope and make it slower, less positive. Growth slows down. It's not that it's going down, at least not during this part. Eventually it's going to start going down. It takes the positive slope and slows it down. So that would be more positive, less positive. How about the bottom right? Which one's this? More negative. A negative function that's accelerating. It's becoming more negative. Or, last one? Less negative. That's it. There's only 4 kinds. Once you figure out which quadrant you're in, then you can talk about it. But to use the coefficient, twice the quadratic is how the linear rate of change changes per unit time. That's the key. Twice. So we started looking at an example, working through these ideas of first fitting the baseline model. So just to review, we have 6 sessions where the outcome is response time. They occur during a 2-week period. So we're looking at just improvements in response time as a function of additional practice with this task, where session is my unit of time. We have a pattern of means that was just shown in the picture, where they go down over time. We're looking for different models to approximate that. Last time we got through fixed linear and random linear, right? So here's fixed linear, model 2A, in which everybody is sharing the same fixed linear time slope. In adding that fixed linear time slope, because time is entirely within persons, everybody has the same set of 6 time observations. Time has an interclass correlation of 0. Because time is completely within persons, it should only explain residual variance, and it does. So we have a little macro program that I wrote in SAS. I also have this as an Excel spreadsheet in example 6, the download packet that I made for you. This goes with chapter 6 from the book, along with some extra material that I'm planning on adding to the next version. It's opening. Think about it. Go. No, really. Please? Maybe I forgot to say please. You know, when my son Huey, he's 4, he asks for something, and he doesn't say please, my standard response that I learned from his teachers is, oh, I can't hear you. He says, please, oh, now I hear you. So please, Excel, please open sometime during my lifetime, please. So the macro program that I wrote for SAS saves the CoveParm output and then does the calculations on it to show you where those calculations come from. I put it in the spreadsheet as well. So we're looking at this right here. So we had a residual variance estimate of 44,900. This is response time in milliseconds. That's why these numbers are so big. After adding fixed linear time, the residual variance at level 1 went down to 35,000 and some change. That is, so I multiplied the R-squares by 100 so we can see them a little easier. It's about 21% of the variance. So 21% of what was within person level 1 residual variance is because people decline, on average, significantly by 52 milliseconds a session. Now, can I claim that time explains 21% of the variance in the model? Can I say I have an R-square of 21%? No. Correct. Why not?
And it's the percent of the residual.
It's the percent of the residual. How much was residual in the first place in this data set? How do we know that? What model would tell us that? Huh? Say it louder. The other one. Yeah, the empty model. Yes, indeed. So I've got that one in here somewhere. Empty means random intercept model. Actually, it's the one right before it. So the V-core matrix gives us the interclass correlation of 0.82. So if 0.82, that's between, that means within is 0.18, right? Doing math in front of you, always dangerous, but I think I got that one. So it's 18% within, 82% between. So if I look at this number right here, what I can say is of the 18% of the total variance that was within persons over time at level 1, Adding fixed linear time reduced it by 21%. So if I want the total R-square for the model, it's 21% of 18%. And I'm not going to multiply that for you, but you get the gist. Right? I can't do that in my head, I'm sorry.
3.6.
Boon. Now, meanwhile, look at what happened to the random intercept. It went up. Anytime you explain residual variance with a level 1 predictor, the random intercept variance must go up. It's because there's less of a correction factor used in trying to distinguish the true between-person variance from the observed between-person variance. How would I talk about that in a paper? I would not. It's not relevant. This is what's relevant, 21%. When we put predictors in a multi-level model, we have to figure out which kind of variance they are supposed to account for. The answer should always be one kind. If it accounts for more than one kind at the same time, that is a problem. That means your model is not specified correctly. In practice, they can wiggle about a little bit, but you shouldn't see any significant changes, any sizable changes. So we reduced our residual variance. So if I were talking effect size versus significance, my fixed effective time, I can use this Wald test, or what we would call a modified Wald test, because this is the t that's using denominator degrees of freedom. That's my significance test. For effect size, I could take this t and turn it into like a d or some kind of r or g or whatever letter you want for effect size. Or I could talk about pseudo r-square for the residual variance. It's up to you. They should converge on the same result. All right, so I think we've hit all the questions on here. This is the output from the little program that I wrote that does pseudo r-square for you. The input to the program, for each model to be compared, you'll need to have saved the covariance parameters from the model. So right here, here's a call to the program. You need to tell it how many model parameters you have in your model for the variance, which is 2 right now, random intercept variance and residual variance. What you called the results from the model with fewer parameters, which in this case was the empty model, and what you're calling the parameters from the model that has more. So this is the fixed linear. So I'm taking relative to the empty model, empty means random intercept model, I'm asking for a comparison of the variance components from the fixed linear random intercept model. So we have the same variance components in both, which means the model has changed in fixed effects only, as is desired to be able to calculate pseudo r-square. Okay. Questions? Any that you need to hear again?
So it makes no sense to calculate the swaths when we have different variance components.
Correct. Yep, when you add something random, you're taking it from 2 variance components to 3 variance components. So what each of these means is necessarily different because they've been repartitioned into 3 instead of 2. So the point of adding random effects, which is what we're going to do next, is not to explain variance. It's to partition it so that fixed effects can better explain variance. So we're adding random linear time. Now we're doing this for several reasons simultaneously. From a hypothesis testing point of view, we want to know if people change differently. The previous model said everybody changed the same. Everybody declined in response time by 52 milliseconds a session. What if that's not true? What if some people improve at a better rate? Sure. So that's the question that's being answered. What we're also doing simultaneously is asking if there's another form of person dependency. Remember, in dependent data, we have to control for dependency. How we do that is by adding variance components. So we have a random intercept that allows constant person dependency due to mean differences. Now we're asking if we also need a random slope that allows non-constant dependency, a dependency that is related to a person's time values. For now, we're leaving the R matrix alone. So within persons, we're saying the E variance is constant over time with no covariance because all the reasons that the residuals would have been related and would have had different variance are supposed to be down here in G. Level 2 between person random effect variances, of which there are now 2. Intercept at 1, 1, random linear time slope at 2, 2. Their covariance in the off diagonal, and here's the correlation version down below. So that correlation of negative 0.53 is specifically among the starting values predicted for each person. So their predicted intercept at session 1, which is our time 0, and their subsequent linear rates of change. If you wanted to report and interpret this correlation, you have to keep in mind where time 0 is, because it will change as a function of where time 0 is. Here's a quick picture to illustrate this idea. This is a depiction of what a random linear model would predict. Different slopes for different folks. So on the x-axis is some metric of time. What if I centered time right in the middle here? Then there is absolutely no correlation between where you are with respect to your intercept at this point specifically and how much you change. There's actually no intercept variance here at all in this picture. If I center time at the end, the correlation between where you are at this point in time on your intercept and how fast you change is positive 1. The people who are the highest have the highest linear slopes, the greatest linear slopes. If I go backwards in time and center time here, now the correlation between the intercepts and slopes is negative 1, because the people who are currently the highest are those who have the shallowest slopes. So which of these intercept-slope correlations is the right one? Any of them, right? They're all right, because they're all describing a different cross-section of what happens. So when you're introducing a random slope of any kind, when you're letting people change differently, the rank order shifts itself accordingly. So if you're wanting to predict, what makes people high on Y at this point in time, that's a different prediction than what makes people high on Y later in time, right? People have rearranged themselves. So the intercept is a different thing at each of these points. It will have a different variance, and it will have a different correlation with the linear slopes. So just be careful if you want to interpret this correlation that you refer to it, in this case, as the predicted intercept at the beginning of the study is correlated negative 0.5 with subsequent rates of change. So now if I want to go in deeper, are people going up or are they going down? They're going down in the study. Okay, so let me put this. So people who start out higher, I want to be at the bottom of the distribution, which means more negative. So people who start out slower have more negative rates of decline. That makes sense because if you suck at this task to begin with, you have more room to improve, right? If you're already fast, you can only get so much faster. Response time can't go negative. So yes, trying to figure out what this intercept-slope correlation means can be tricky because what does change mean? So what does high versus low on change mean depends on which way you're changing. In this case, if I were to draw sort of my depicted slopes, the ones at the top are going to be the shallowest, which means they're changing the least. The ones at the bottom are going to be changing the most. So higher intercepts at time 0 go with more negative change in this case. So what this addition of a random slope variance and its covariance with the intercept, we added both of those things at the same time. What this does then is build a V matrix, a total, that allows the variance to change systematically as a function of time. So this model predicts not only what the variance would be at exactly session 1, exactly session 2, exactly session 3, but it also is capable of predicting what the variance would be at time 2.5, right? Because it's a continuous function that's giving you the variance at any predicted time. Likewise, it predicts what the covariance should be based on the fact that it's session 1 and 2, 1 and 3, 1 and 4, and so on. But it could, is it interpolate? Is that the word? When you fill in between the dots? Yes, the right word? That's what I thought. Interpolate. It can interpolate between these things as well. So this is the predicted V matrix for person 101. That person has sessions 1 to 6 as integers. If someone else, the next person, had different values, they'd get a different V matrix. But everyone's V matrix is built from the same G matrix of level 2 random effect variances and covariances, the same level 1 matrix of residual variances and covariances. The only difference is the time values that are put in to make the predictions. Yes?
I have a question about the interpretation of the correlation between the slope and the intercept.
Yes.
So it's negative, so I would think, okay, the higher the intercept, the more negative is the slope. So the higher you start, the faster you decrease.
Yes.
That's the interpretation.
Yes.
Ah, okay. Okay.
Yes, if I didn't say that, that's what I meant.
Okay. Maybe it's not.
Yeah, it's hard because you just want to say, well, more change. And it's like, well, what's change? Is change more up or change more down?
So if it was positive, it would mean that it still decreases, but less. Like
yeah, so if, yeah.
You are, the less you decrease, but you decrease less than if you are lower on the intercept.
If change was positive, it would mean that people who start out higher change the least. Yeah, okay. It would be backwards. Mm-hmm. Yeah, it's tricky to figure these out. But yes, I think we got it this time. Okay. This thing right here, null model likelihood ratio test, that thing tells us, can you guess? Degrees of freedom 3, what is it telling us? I'll give you a hint. It's not anything I care about, but it's here.
Does it compare the null model with the empty model? With the model with
empty with respect to what?
With respect to fixed effects. Like the model with only random intercept?
Not quite, but you're on the right track. It tests the whole G matrix. So it keeps the fixed effects the same. It compares it to a model where the model for the variance is E only. So it's testing the whole set of person dependencies in the G matrix as a whole. It's testing these 3 things right here. So given that we already know that we needed a random intercept, what we really want to know is, do we need a random slope too? This omnibus test that lumps the intercept and slope together doesn't really help us. So you could report it. I don't know what question it answers that's helpful. Instead, what I want to know is, relative to the model where each had a fixed linear term, does the model that adds random linear fit better than the model that has only random intercept? That's what I want to know. And are you allowed to stare at this p-value right here and go, yep? No. And by no, I mean there's like 10 people who know about the difference and care enough to yell at you for it. There's actually some really bad multi-level modeling books that tell you to stare at the p-value. Yeah, here's the dirty little secret. There's no quality control on books. You can write whatever you want. I'm not kidding. I have a book, I know. Because they sent out chapters for review, and so I contacted my editor and I'm like, okay, so do I respond to the reviews? And she's like, nope, this is just some feedback for you to consider. I'm like, oh, So this person could tell me, I don't know anything about what I'm talking about, and I'll be like, thanks for your input. So I'm going to keep going. So yeah, that's part of the reason why books are not as thought of as highly in academia, at least in our field, as peer-reviewed papers, is because they're not really peer-reviewed. So yeah, there was a book that I got to review where they said, yeah, look at the p-value, and I said, no! And it's in print, because they don't have to listen to anyone. But yeah, so no, we can't do this. In practice, I would say that, yeah, I'll eyeball this and think it's fine. But the problem is that variances can't go negative. So this idea that you can take the estimate and go 2 standard errors around it and come up with a significance test based on that, variances aren't normally distributed most of the time. And they're especially not as they get closer to 0, which is when you'd care about the significance test. So yes, even though this is here, ignore it. The right way to answer the question as to whether or not we need a random linear slope is this piece of output right here that came from my macro likelihood ratio test. So to use this, there's a macro called fit test where I put in the information criteria table, that's this thing right here from the previous model, versus the one from this model. So up when I ran the model, it shows up right here. This ODS output statement saves the covariance parameters piece of output in the data set. It saves that information criteria table in a data set, stacks them on top of each other, and does the math for you to do the likelihood ratio test or the pseudo R-square. I also have it built into Excel. Because why not? So that's our first one here. So -2 log likelihood. Smaller is worse or better? Better. Yeah, log likelihood bigger is better. Once you multiply it by -2, smaller is better. So I had a model that had 4 parameters before, fixed linear random intercept. I added 2 when I added the random linear slope variance. Why 2? What's the extra one? Yeah, the covariance between the two. It comes along for the ride. Don't ever not do that. It always comes along for the ride. So 2 degrees of freedom, 42 is my critical value. Okay, so I write this up and I turn it in paper, and reviewer 3 says, excuse me, this is not the appropriate hypothesis test for a random linear slope. You should be using a mixture chi-square distribution. Remember we talked about this last week? Okay, what do I say? Dear reviewer 3. First sentence, always, remember?
It's my fault, Alex.
I am sorry. I apologize for not being sufficiently clear. It is always your fault. That is the first sentence, always. As now clarified on page 13, how do I make this person happy? Now, first question, does this matter at all in this case?
No.
No! What they're yelling about is that the critical value for 2 degrees of freedom is 5.99, and it really should be 5.14. That's what they're yelling about. It's 42. So forgive me for just, it's 2, fine, right? And not wanting to explain a mixture of 1 and 2. But if you get that, put the footnote in that, it should be a mixture, but you're using 2 because it doesn't matter, or you're using 2 because it's slightly more conservative and you're okay with that, or just get the p-value that goes with the mixture, and my guess is that it will still be 0 to like the 5th decimal place. So, in this case, it doesn't matter. Occasionally it will matter, and you should know the difference. All right. So now, I have a question here. Do we need to compute pseudo R-square? The fact that I didn't do it should clue you in. I added random linear. Do I do pseudo R-square to talk about its effect size? No. No, when you add random things, you're not explaining variance. You're repartitioning it. So we had a model previously that only had random intercept variance and residual. Now we have a model that also has this new pile of variance to be explained, random linear time slope variance. So even if I wanted to, I don't know how to go back to the previous model because it's a 2-pile model and now I have a 3-pile model. So I do have a significance test if I want to try to convey effect size. Here's an idea for how to try and convey that. This is a confidence interval, or interval as has been suggested, but this is what Snyders and Bosker said. So they describe the variance of the intercepts and the slopes in the sample. So the middle of each of these intervals is the fixed effect, so fixed intercept or fixed slope, plus basically 2 standard deviations around it, where the standard deviation is given by the random variance that goes with it. Intercept variance here, time slope variance here. So if I look at these numbers, I can say, not only is my random linear time slope variance significant, but what it means is that on average, even though there was significant change of 52 milliseconds a session, that was predicted to be, in my sample, anywhere from about minus 145 all the way up to 42. So it's a way of putting this back into the metric of the original variables. This is change in response time per session. This is how much it ranged in my sample according to the predictions of my model. And if I'm talking too fast for you, this is all written down in the back of chapter 6. There is a results section where it's probably word for word because I only know how to explain things in so many ways. But that's where it is. So another thing that I'm not doing at this point is talking about pseudo R-square in terms of reference back to a total. So you know how when we added fixed linear time, I could say, of the 18% that was within persons, I explained 21% of that. I can't do that anymore. The problem, why I can't do that, is right here. There is no way to add up these variance components into some sort of total because the intercept and slope have a covariance. So I can't put them back together again because they're not orthogonal. For the same reason, if I wanted to talk about intraclass correlation, I could calculate it. I could still take my random intercept variance over random intercept variance plus residual, but it is only going to hold at time 0. It is a conditional, specific intraclass correlation for time 0. It would be some other number that would have to incorporate these 2 other components, the intercept slope covariance and the slope variance, if I wanted it at a different time. All right, how are we doing? Okay. Any that you want to hear again? Ask questions about. Okay. Now, finally, something new and cool, quadratics. Yeah, I can't even tell you how many people have said, well, we don't interpret the quadratic because it's too hard. You do, starting now. It's not hard. You just have to know how to do it. Twice the quadratic, that's the answer key. So I'm adding quadratic time to my level 1 model. That means I'm picking up a 3rd beta, which means I have a 3rd level 2 equation. So far it's fixed for everybody. Everybody shares the same rate of acceleration or deceleration. I have put it in my model as time by time here. So you don't have to make a quadratic variable if you don't want to. And then I've asked for a whole bunch of predictions here to illustrate the many, many uses of the estimate statements and help us understand what this quadratic is doing. So let's focus in on the first set here, intercept at each occasion. What I'm asking for are model predicted values based on the fixed effects. This is exactly what you learned how to do in a regression class, hopefully, right? How to calculate for any combination of x's what y is supposed to be. That's what this is doing. but it's doing it via code so that you get not only the predicted calculation, the estimate, but the standard error and a p-value for it. So the way to interpret these statements is that each of these words actually refers to the fixed effect that goes with it. So I like to think of this as somebody who's driven up to a drive-through window, drive-through windows to get fast food. Even though they know they're there to get lunch or dinner, it's like they've never thought about what they're going to order. And so you're inside listening to them. It's like, yeah, can I get like a double with cheese, onion rings? No, shh, I'm talking. Right, it's like this long drawn out process. So this is kind of a long drawn out process. Think of it the same. It's like, yeah, I need an intercept at time 5. So can I get 1 gamma 0 0, and I need a 5 gamma 1 O's because it's for time 5 where session is 6, and because 5 times 5 is 25, I'm going to need 25 gamma 2 O's. Will that be all? Yes, please. Drive around. How's that? Yeah. Now, what's not in here? Any reference to random effects. So this is going to generate the same prediction for everyone for what their predicted random response time is at session 6. You can actually add random effects if you want to. If you wanted to get the prediction for person 12, there are ways to do that, but that's not typically of interest. But this is how I would generate points to make a plot. Now what's happening down here is different. This is a request for simple slopes of an interaction term more generally. And in this case, what I want is the instantaneous linear rate of change at each unit of time. So in calculus terms, I'm asking for the slope of the line that's tangent to the curve at that point. So you can think of it as the slope at each point. It's not correct to think of it as the slope like from 1 to 2 to 2 to 3. No, it's at 1. That's the way to think about it, instantaneous. So what goes into a slope? Not the intercept. That's not here. What I need to know is for what occasion you want the slope. So each of these statements start off with 1 gamma 1 O, because at the minimum, that's what my fixed linear slope is going to be. Then I need to tell it how to modify it given the quadratic. And how I modify it is twice. So 2 times the time value for which I want the prediction. So the twice part is the part that's not as intuitive because this is the only situation in which that shows up. Normally you would just plug in the value for the moderator, which happens to be time. But in this case, because there's not another main effect in the line, we have to have it twice. So twice the value of time for which you want the instantaneous linear slope. The model is already going to give us this one. That's what gamma 0 0 means. And it's already going to give us this one. That's what gamma 1 O means, the fixed linear slope. Why did I write these? So you could see the patterns better. And because it's convenient if all the numbers you want to look at are in one section. I also refer to these sorts of statements as my trail of breadcrumbs. When I'm really, really deep in a model and I want to know what I meant 2 years later, having these things written out, very helpful. Plus it creates output that you can easily hand to somebody and not have to explain too much what it means. Okay, with me? All right, so let's see what happened. So which variance component should have been reduced by my new fixed effect of quadratic time? 3 choices: E, U0, or U1. I guess? I'll make it easier for you. Is time a time thing or a people thing? Yeah, it's a time thing. Which kind of variance is time-specific variance? It's E. So E should go down. So within-person variation should be reduced because now we've tried to draw a better line. A line that's bendy instead of straight. So indeed, my residual variance, let me get my spreadsheet out here to refer back to things more easily. Here we go. Here's my two comparisons. Previous model was random linear time relative to fixed quadratic random linear time. Residual variance did indeed go down by 6%. It's tempting to try and come back to this as some sort of anchor point, but we can't because now we've picked up another type of residual variance here, the random linear slope variance. So it's of the residual variance that remained after giving each person their own intercept and slope, another 6% was accounted for by adding fixed quadratic time. So it can be very tricky to word this in a way that conveys the new partitioning and what things are relative to. And because the residual variance was reduced, random intercept variance went up. And so did random slope variance because the two are correlated. The intercepts and slopes are correlated. So 6%, does that sound like something that would be significant? Okay. Let's find out. Depends on your sample size, right? Survey says, indeed, wall test, we can stare at that one. Now, which of my four patterns is this one? So let's walk through this here. Intercept, come back, Mr. Mouse. It always extends onto this other desktop and then I lose my mouse. Come back. There, found it. Phew. Intercept. That's my predicted response time at time 0, which is session 1. So the interpretation, that sentence, is the same from the previous model, but the number has changed because what predicted means has changed. Previously, it was 1900 because it was predicted from a straight line. Now it's 1945 because it's predicted from a bendy line. From there, the fixed linear slope used to be minus 52. Now it's minus 120 because it means something different. Minus 52 was the average rate of change over time. Minus 120 is the linear rate of change, ... At time 0, which is session 1. So at the very beginning, that slope. Here. Slope at the beginning. It's going to eventually level off. That first slope is minus 120. Now, what does the quadratic say is going to happen to it? Yep, that's correct. Now put some words on it. Which are my four patterns? More positive, less positive, more negative, less negative?
Less negative.
Less negative. By how much per session, and don't say 13? Times 2. So 27-ish. So putting that all together, the predicted rate of change at session 1 is 120 milliseconds a session. The quadratic means that rate of change is expected to become less negative or to slow down by 27 milliseconds for each additional session. And this is where the predictions that are next help us understand what's happening. In particular, the linear slope instantaneous predictions from this model. Minus 120, that's the one we just got. The next one, 27 less negative. The next one, 27 less negative, 27 less negative, and so on. So the gap between each of these predictions is exactly 27. Or 27 and some change. My point is that it's constant. The way the linear slope slows down is the same over time. The quadratic is the highest order term in the model. So this provides potentially useful information if you want to think about when change kind of shuts off, according to this model. So if you were trying to develop a protocol for what is the optimal number of sessions, you want people to get as good as they're going to get but not drive them crazy. Do we need 2 sessions? Still improving, yes. 3? Still improving. 4? Somewhere between like 4 and 5, right? That's when the slope is predicted to kind of stop. And they actually start heading the wrong way, because that's what the quadratic predicts, right? Now that might actually be reasonable in this case if they're really tired of doing this by the end and they're like, ugh, please stop asking me to do this. But that's a whole separate phenomenon. And then here are the predicted means over time, where you can see the successive differences are reduced as time goes on. One other thing to note, the difference in the standard errors for these instantaneous linear slopes, they're always going to be the smallest in the middle, because that's where we have the most precision. Sometimes people advocate mean centering time so that linear time and quadratic time are as uncorrelated as they're going to be to try and reduce collinearity. That's not strictly necessary, but just keep this in mind as you're trying to make predictions that some of these numbers are being estimated better than others. All right. So here's my pseudo R square, 6%. We talked about that. All right. How are we doing? Good? I don't need to get my stick out, do I? Everyone still awake? Okay. Then we're ready for random quadratic, the big enchilada. Okay. Quick review. Previous model with fixed quadratic, random linear. How many sessions do I need at a minimum to make this estimable? Let's take it one side of the model at a time. If I have fixed quadratic, that's fixed intercept, fixed linear, fixed quadratic is my fixed effects. How many occasions do I need? 3, right? At a minimum. Now how about the variance side? I've got random intercept, random linear, covariance between the random linear and the intercept, and residual. How many do I need? 4. Yeah. So to pull this off, I need 4. I only need 3 occasions for the fixed quadratic, but I need 4 for the random linear part. Random intercept, random linear, covariance, and residual. Now, if I want to add random quadratic, I need how many? Hang on, I said that wrong. Wait, I only need 3. I was already on this model. I need 4. I need 3 for that one, and I need 4 for this one. Here is, I was on the wrong one here. This one. This is what I'm referring back to. I can do 1 random slope if I have 3 occasions. If I want to do 2 random slopes, I can have 4 occasions. So thank you for looking at me like that, Bitlin. Like you clued me in that I was saying something wrong. She's like, I don't think so, but okay, keep going. Yes. I am fallible, as it turns out. I'm prone to saying things the wrong way when I'm trying to think and talk at the same time. It's tricky. So yes, we need 4 to pull this off. So we've added quadratic time to the random line. That means G is 3 by 3. So how many total parameters have we added in asking for a random quadratic time slope? And don't say 1. It's 3. Variance? covariance with the stuff that's already there. An easy way to remember that is to look at the number of items on the random line, and that will always be your degrees of freedom for your change in the model. So let me say that differently. If I go with a model where it's random intercept versus nothing, that's 1 degree of freedom because I have 1 thing on the line. If I add this, now I have 2 things on the line, that's 2 degree of freedom change. If I put the quadratic in, there's 3 things on the line, that's 3 degrees of freedom. If I put time to the 4th, now there's 4 things on the line, that's 4 degrees of freedom. So it always works when you have an unstructured random effects G matrix. Okay. So is it significant? Likelihood ratio test to decide that. Difference of 38 on 3 degrees of freedom, or what should actually be 2 and 3 is a mixture, but again, the difference in the critical value is such that it doesn't matter. We're not computing pseudo R-squared, but we are computing random effects confidence intervals to talk about the intercept, linear slope, and quadratic slope variability. So let me give you a picture then of where we're at. So we've considered 4 models. So this picture from chapter 6 is predicted response time on the y-axis, where the x-axis has the first 6 sessions, but then also predicted sessions into the future, what the model says should happen. So we have the answer key, which is the black line with the squares. We know what really happened. We have the empty model that says there was no change. We have the linear model that says change keeps going forever and ever and ever, and eventually they'll have negative response times. Nah, maybe not so plausible. Now we have our quadratic model that looks like it does a pretty decent job capturing the trajectory, but it says that people should start getting worse if we let them keep going. So how do I know if this is good enough? How do I know if I should stop? You know one way, and I want to teach you another. What's the one way you know that you're going to get a chance to practice on homework 5? 4? 5? Whatever one you're up to right now. The one that's due tomorrow. How do I know if the model that has these 6 means fits better than the predicted means from my quadratic model? I could do a model comparison, so long as I was using what to estimate the models? Emil or Remel? Emil, regular flavor, but I'm not using that. So rather than switch estimators to go do a different test, we can do a different type of model comparison using a multivariate wald test. And so this is bonus material that's not in the book that I wanted to share with you because it will be in the book the next time. So it looks like this is our best fitting model so far. Everything that we've added to this model has improved it significantly. If we had thought that this was going to be our best model to start with, we could have started with this. Rather than building all the way up step by step, we could have started with this and went backwards. Right? If you start with random quadratic, take out the random quadratic and do a model comparison. If it's significant, then you need it. If you need random quadratic, you know you need fixed quadratic. If you have random quadratic, you know you need random linear. If you have random linear, you know you need fixed linear. So you know you need everything else that's under it. So there's nothing that stops you from starting at the most complicated model and working your way down, or starting at the bottom and working your way up. I prefer the latter for pedagogical reasons, but in practice I may go the other way. But the question I'm trying to get at here is, how do you know this is good enough? I have 6 means. I've spent 3 degrees of freedom in trying to fit them. Fixed linear, fixed quadratic, fixed intercept. I'm going to do a model comparison, sort of, but I'm going to do it by adding additional fixed effects, not by doing -2 log likelihood difference, so that I can stay in REML. And here's what I'm going to do. This right here. Session is going back in. Now on the surface, this looks crazy. What I'm asking it to do is to estimate the extra 3 parameters that I didn't spend. Essentially plug the holes that are left between the saturated means and the means predicted by my model. And SAS figures out by itself how many holes there are and estimates that many parameters. So now it put in 3 contrasts. So I have 6 parameters that are perfectly replicating my 6 means. The other ones, it didn't estimate because it can't. Now what the intercept, linear slope, and quadratic slope mean has changed because of these additional contrasts. We don't care about the former part of the model, we care about the new part. And in particular, we want to know if this set of 3 contrasts has helped the model or not. So this is the one instance in which I found it useful to revisit this whole types of sums of squares thing. Remember type 1 versus type 3? I was pretty rusty on that, but it's sequential versus not sequential. You can ask it to change which type it is. 3 is the default, but I'm asking for type 1 here, so that all these tests of session here, the extra 3 contrasts, are over and above the model as it used to be. So this F-test right here is a multivariate wall test of the set of additional contrasts that plug in the holes between my model predictions and the right answer. So the fact that those 3 degrees of freedom have a significant F value means that we need them to plug in the holes. It means my model does not have absolute fit. It does not fit as well as the 6 means. It fits significantly worse. This is only possible to do in balanced data. You have to have the answer key model to come back to in some way, shape, or form, either by adding extra contrasts or having the saturated means model. So I could add cubic, right? I could keep going, but quadratic sort of didn't make sense to begin with. Why do I want to keep going? Let's find a nut. Let's find something else. Right? It's like you're out shopping and you try something on and you're like, do I need a bigger size? Do I need a smaller size? Like let's just try a new dress, right? This isn't working. Okay, so this is like the most optimal we can do. It's not working. We'll go with something else. Same idea on the variance side. So here's what the variance predictions are. I just plotted the variances, but the covariances are part of the story as well. So this picture, the y-axis, is the variance and response time in each session, up to 6, and then predicting into the future. Random intercept only, same variance over time. Answer key, solid line. That's my unstructured model for the variance. The triangles, that's the prediction from the random linear model. You can see that it's quadratic. The prediction from the random quadratic model is this crazy line that looks normal until it shoots into the sky. And I actually it's way off the chart. I just truncated the chart. It's a quartic function, so it predicts that variance explodes and goes insane after this is over with. So is this quadratic line close enough? We know it's better than random linear because it fit better, but is it close enough? To answer that question, we can do a likelihood ratio test. So I'm going to re-estimate the same model of fixed effects, fixed intercept, fixed quadratic, and change it to type equals UN. I have to keep the fixed part the same because I'm in REML. So I'm just looking at the variance side. Given the same fixed quadratic model for time, Do my random linear and quadratic time slopes do a good enough job approximating the total variance covariance matrix? Survey says no. Unstructured is significantly better. So again, the reason that I'm taking this absolute fit test in 2 parts is because of Remmel. We have to have the same model for fixed effects in order to test differences in variance. And we can't do likelihood ratio tests for models that differ in fixed effects. So a way around that is to test each part of the model separately. And it comes to the same conclusion. This model doesn't fit. It's as best as we can do within the family of polynomials, but it's not good enough yet. Now, what if the problem is not just the random slopes, but also the e's? Remember our R matrix looks like this, right? Do we have to have it looking like that? No, we can add some stuff to it. Maybe this is the problem. In particular, maybe the e's that are close together in time still have some sort of covariance that should sit in there in addition to the random effects. Well, that's a reasonable question. So let's test it. So let's switch it out to AR1. So here's my estimated R correlation matrix. So the AR1 parameter was estimated at 0.17. So occasions 1 session apart in time are correlated 0.17. 0.17 squared gives us 2 occasions apart. To the third gives us 3, and so on. Likelihood ratio test to see whether or not that is significant. Survey says adding 1 AR correlation parameter, nope. Now this is an instance in which you'd want to pay attention potentially to this mixture chi-square thing. However, can correlations be negative? Yeah, they can. So this isn't on a boundary. So it's 1 parameter, but you can argue that this is 1 degree of freedom is accurate. So how about toplets? Let's add a covariance between adjacent occasions only. It's estimated as a correlation of 0.12. Model comparison says, does that help? No. So that's not heading us in the right direction. So putting it all together, so far, 6 occasions, change in response time. People decline over time, but non-linearly in some capacity. They become more homogeneous over time. People's scores get closer together. I've thrown the best fitting polynomial model that I can think would be reasonable at it, and it doesn't fit. Time to change strategies. So that's where we're heading next. 3 other strategies that are in the rest of this handout. Piecewise slopes models, or I'm going to try and approximate it with 2 discontinuous slopes. Negative exponential models, which is a truly nonlinear model, in which case we're going to have to use a different software package. NL mixed. Have you guys seen anything like that before? Where you write out the model? Yeah, it's kind of like R-ish, like it's much more codey. But yeah, we'll do some negative exponential models. And then last but not least, I will teach you a cheaty way to get to a negative exponential model by taking time and log transforming it, because it mimics an exponential curve pretty darn well, and it allows us to use Remmel. So those are the 3 places we're headed next. All right, questions? Okay, I have office hours now until 3. Let me know if you need help with your homework. Otherwise, it's due Friday, and I will see you all next week. Or no, I won't. Enjoy catching up on your work, your laundry, your sleep, and your life. And I will see you a week from next week, Tuesday, week and a half.